In order for students to solve energy conservation problems, they need to be proficient with both qualitative and quantitative tools. Before jumping to equations, students first need to be able to identify where the energy is being stored before and after a certain event. Some qualitative tools which help students represent where energy is stored include energy pie charts or energy bar graphs. These qualitative representations can help students create an energy conservation equation for the given scenario. Once the energy conservation equation is found, students can simply substitute the algebraic equation for each energy storage account and solve for the unknown. In this video, I will walk you through an introductory physics lab that allows students to develop a model for the relationship between an object's kinetic energy and its velocity. This guided investigation will allow students to develop the kinetic energy equation, where the kinetic energy of a moving object is equal to 1/2 times the object's mass times the velocity squared, or K equals 1/2 mv squared. Before starting this lab, students need to be familiar with making energy bar graphs and calculating a system's gravitational potential energy. You can find all the lab equipment needed to do this investigation at arborsci.com. At the start of the pre-lab discussion, review the basic representational tools and energy equations that have been discussed in class. Just like equations to calculate the spring potential energy and gravitational potential energy, tell students they will need an equation that allows them to calculate kinetic energy, the energy stored by moving objects. For the pre-lab discussion, you can use the car and ramp lab equipment and the timer and photo gate found at Arbor Scientific. This is the same equipment that can be used by students for data collection. While pushing the low friction car on a level track, ask students what measurements or variables they think are related to the amount of kinetic energy stored by the moving car. What can be changed about the car that might change its amount of stored kinetic energy? If students already have experience with energy bar graphs, they already understand that faster moving objects store more kinetic energy and vice versa. They might just need to remind themselves of this fact. Tell students they're going to do a lab investigation that finds out how an object's kinetic energy is quantitatively related to its speed or velocity. This will give them an equation that will allow them to calculate the amount of kinetic energy stored by a moving object. Write the following purpose on the board: to determine the relationship between the kinetic energy of a moving object and the object's velocity. Now you can help guide students through a procedure for collecting the needed data. To determine the relationship between the kinetic energy of a moving object and the object's velocity, the students will need to collect a variety of different velocities and the kinetic energy stored at each measured velocity. While pushing the low friction car on a level track, ask students how the car's velocity could be measured. Students will often mention using a motion detector to directly measure the car's velocity, or a meter stick and stopwatch to calculate the car's velocity. During this discussion, I introduce my students to photo gates, which can also be used to measure the car's velocity. A photo gate has the advantage of being able to measure the car's instantaneous velocity at a specific position. Technically, the photo gate is measuring the car's average velocity over a small displacement while the beam is blocked. This average velocity is very close to the car's instantaneous velocity as part of the car moves through the photo gate. Now that students can easily calculate the car's velocity, they will need to figure out how they can measure the car's kinetic energy. Ask students what they can do to transfer a measurable amount of kinetic energy to the car when it moves through the photo gate. Students typically come up with two different scenarios. Scenario 1 involves using a compressed spring to launch the car on a level track. In this scenario, the car's final kinetic energy is equal to the initial potential energy. Scenario number 2 involves elevating one side of the track to make an incline. When the car is raised above the photo gate height, students can calculate the amount of gravitational potential energy added to the car and Earth system. Assuming friction is negligible, this initial gravitational potential energy is equal to the car's kinetic energy when it passes through the photo gate. For this video, I will discuss the second scenario. Remind students that the final kinetic energy is equal to the initial gravitational potential energy only if the height of the car when moving through the photo gate is considered to be a height of 0. This means that when students use the gravitational potential energy equation, they will have to use the car's change in height from the defined height as 0, rather than just the car's height from the table's surface. Also, it is helpful to have the students measure the car's height from the same point each time. Students find it easiest to measure the car's height using one of the car's axles. Just to review, students will use the measured change in height to calculate the initial gravitational potential energy. The car's kinetic energy when moving through the photogate will be equal to this calculated gravitational potential energy. And the car's velocity is found using the timer and photogate. In order to collect more kinetic energy and velocity measurements, the students will place the car at different heights along the incline. Make sure that students collect a wide range of values using small and large heights on the incline. To introduce some variability in the collected data, instruct half of the lab groups to add 150 grams to their car for the entire experiment. This variability will help the students reach conclusions about their graphs and equations. To analyze the collected kinetic energy and velocity data, have the students graph their data by placing the kinetic energy values on the y-axis and the velocity values on the x-axis. Students should find that the graph data will produce a top-opening parabola with a y-intercept close to 0. In order to write the algebraic equation for the relationship between the kinetic energy and velocity, the students will first need to linearize or re-express their nonlinear graph. In my class, this is a skill that was introduced in a previous lab. To hear a more detailed explanation of re-expressing or linearizing a nonlinear relationship, check out my previous video from the Cool Stuff blog at arborsci.com. Sometimes when students look at the original kinetic energy and velocity graph, the trend will appear linear. This will typically happen if the students do not collect a wide range of values. Upon closer inspection, there's usually a slight upward curve to the data, but the students are not convinced it is parabolic. When looking at graphical trends, I tell students to look at both the visual pattern of the data and to think about the expected value of the y-intercept. Ask students what they expect the y-intercept should be. All students will say that they expect the car's kinetic energy should be 0 when its velocity is 0. This means that their graph should have a 0 y-intercept. If a data point is placed at the origin, the students will see that the graph is parabolic and will need to be linearized. To linearize a top-opening parabolic graph, the variable graphed on the x-axis needs to be squared. When students graph the kinetic energy versus velocity squared, their graph will appear linear with a y-intercept close to 0. If necessary, remind students how they can write an equation from their linear graph showing the algebraic relationship between the kinetic energy and the square of the velocity. Encourage students to try and simplify the slope units from their linearized graph. Remind the students that a joule is equal to a newton times a meter, and that a newton is equal to a kilogram times a meter divided by second squared. Before the students circle up to share the analysis of their results, ask each lab group to discuss the shape of the original graph and the significance or meaning of both the slope and the y-intercept of their linearized graph and equation. To facilitate a whole class conversation about the relationship between the kinetic energy of a moving object and the object's velocity, have each lab group record their original graph, linearized graph, and resulting equation on a large whiteboard. Here's an example of what one lab group's whiteboard would look like. Have the class circle up so that everyone can clearly see the graphs and equations on each whiteboard. Remember that your goal is to help facilitate a conversation that allows your students to make connections and draw conclusions from their graphs and equations. Start by asking students to compare the graphs and equations on the whiteboards and identify any similarities or differences they see. Since lab groups use different mass cars, the students will be able to identify similar graphical shapes and y-intercept values, but different groupings of slope value. The lab groups who used larger mass cars will have a higher slope value than groups who did not add mass to their car. This will be helpful when students discuss the meaning of the slope. Once the similarities and differences are identified, the rest of the conclusion discussion should focus on the meaning of the slope and the significance of the y-intercept from the linearized graph and equation. When students look at the values of the y-intercepts, they will have small positive or negative values. The question becomes whether these values are significant or insignificant. The y-intercept of the linearized graph can be considered insignificant if it can be reasoned away. Have the students think about what they would expect the kinetic energy to approach if the value of the velocity squared approached 0. Through a guided conversation, students will be able to identify that the velocity squared value will approach 0 as the velocity approaches 0. And as discussed before, all students will say that they expect the car's kinetic energy should be 0 when its velocity is 0. Since the y-intercept can be reasoned away, it can be left out of the algebraic equation. When students look at the slope of the linearized graphs and equations, they should find two groupings of values. Ask students why there are two groupings of slope values. If students can determine the cause of different slope values, this will help them determine the meaning of the slope. Start by reminding students that the slopes of their linearized graphs are constant. This is true for any linear relationship. So this means that the slope must represent something that stayed constant during each trial in their experiment. This constant thing must also explain why groups got different slope values. Discuss each shared idea to help students decide if this is the meaning of the slope. If students simplified the slope units, they should find that the slope only has units of kilograms. This suggests that the values represent a constant mass. When students compare their slope value to the car's mass used in the experiment, they should find that the slope is not equal to the car's mass. The slope value is approximately equal to 1/2 of the car's mass. After the students reach a consensus about the meaning of the slope and the significance of the y-intercept, you can write the general equation on the board. The general equation shows the relationship between an object's kinetic energy, mass, and its velocity. With this equation, students now have all the quantitative tools they need to complete introductory energy conservation problems. To hear a more detailed explanation about the energy bar graphs used in this video, visit my YouTube page, Debbink Physics, and search for energy bar graphs. There are several videos that discuss how to make an energy bar graph when the system is defined differently and when friction is either considered significant or negligible. If you're interested in learning more about these types of guided inquiry labs used in the modeling method of instruction, visit www.modelinginstruction.org. Happy investigating!